Hi, I'm Hiroki Yamada. I'm talking about our paper called ScalarDB, Universal Transaction Manager for Polystores. This is a joint work with Toshio Suzuki, Yuji To, and Jun Nemoto. We're from a startup called Scalar, based in Tokyo and San Francisco. We're now living at the era of managing multiple disparate databases. Since one database does not fit all, there are many purpose-built database products out there. For example, AWS provides more than 10 database products in their cloud service. Also, we have seen many cases where there are separated databases based on microservice architecture. Moreover, large enterprises tend to have siloed databases to support agile business operations. Our goal here is simplifying the complexity of managing multiple disparate databases by having a federated transaction manager. So ScalarDB is a new federated transaction manager. Since such federated database systems are evolved based on new demands and now called polystores, we could also call ScalarDB a universal transaction manager for polystores. ScalarDB achieves global transactions across multiple disparate databases. It also supports various kinds of databases, not only relational databases, but also NoSQLs like Apache Cassandra, Amazon DynamoDB, and Azure Cosmos DB. ScalarDB is designed to meet the following design goals: database agnostic property as the top priority goal based on our customers' need. So ScalarDB global transactions should span various kinds of databases. Strong correctness, which specifically means ScalarDB should guarantee ACID with strict serializability. Reasonable performance, managing global transactions should not be the bottleneck of overall transaction performance. And also high scalability and high availability. So transaction performance should scale as the performance of the underlying databases scale, and managing global transactions should be achievable without a single point of failure. The approaches for achieving global transactions can be categorized in two ways: multi-level transaction management approach and a single-level transaction management approach. The multi-level approach achieves global transactions by coordinating transactions at the coordinator in cooperation with the transaction managers of underlying databases. On the other hand, the single-level approach achieves global transactions by managing and coordinating transactions only at the coordinator and does not rely on the concurrency control mechanism of underlying databases. There are pros and cons in these approaches. First, as a pros of the multi-level approach, there are several real-world products based on a standard specification called XOpenXA. So they are matured. Second, the approach makes the system easy to improve performance because much of the work is done in the underlying databases. So increasing the performance of underlying databases would increase the overall performance. But there are some downsides. First, this approach is too dependent on specific database capabilities, such as concurrency control. So it cannot span various kinds of databases, such as NoSQLs. Also, this approach is invasive, so it requires underlying databases to be modified or enhanced most probably. On the other hand, the single-level approach does not request underlying databases to have concurrency control mechanisms, so it's not very dependent on specific database capabilities. So as a big benefit, this approach could span various kinds of databases. Also, it's not invasive, so it doesn't require underlying databases to be modified. However, there are some downsides. First, existing approaches are only research prototypes, so they only guarantee weak isolation, such as snapshot isolation, or limited isolations, like transactions cannot span multiple partitions. And it's hard to improve transaction performance since the top coordinator does not know how the underlying databases access data due to the abstraction. After a careful study of the different design choices, we decided to go with a single team approach in ScalarDB and try to address the downsides of the approach as much as possible. The main reason for the design choice is that the requirements for the multi-level approach are too strict for underlying databases. Specifically, it is essentially difficult to achieve database agnostic property, which is our key design goal. Here's the architecture of ScalarDB. ScalarDB abstracts underlying databases by using a database abstraction, and it builds a transaction manager on top of the abstraction based on a single-level approach. The abstraction requires each underlying database to provide minimum capabilities like generalizable read and write on a single record and durability of written records. The core component of ScalarDB is licensed under Apache 2. The transaction protocol of ScalarDB is basically a variant of two-phase commit, but it does two-phase commit over records that are abstracted in the same manner. Specifically, it treats single record as a small database and then do 2PC over records, which respectively has its own role information. Also, ScalarDB employs single-level optimistic concurrency control, and the conflicts are detected by using generalizable conditional writes of underlying databases. So let's look at how it works in a little more detail. So when ScalarDB is ready to commit, it holds read and write sets in its memory space. First, it prepares records with the read-write set. Each record ScalarDB writes is composed of application columns managed by users and transaction metadata managed by ScalarDB. We use the same abstraction in all the databases ScalarDB supports, so from the ScalarDB's perspective, there is no distinction between databases. So once records are properly prepared, ScalarDB commits the transaction by writing a record in a table called coordinator table. The coordinator table is a place where ScalarDB manages its transaction statuses, and then it's a single source of truth about transaction statuses. So once committed status is written for a transaction, the transaction is regarded as committed. After that, ScalarDB commits records by updating the statuses of the prepared records from prepared to committed. This is briefly how ScalarDB executes transactions across multiple different kinds of databases. The protocol is similar to the Cherry Garcia protocol proposed in ICD 2015, but we have extended the protocol in several ways. First, the Cherry Garcia protocol depends on reliable clock, specifically true time for correctness. But you know, true time is not always available, so depending on it causes applicability issue. Also, managing a reliable clock with a timestamp oracle is challenging if we need to achieve high scalability and high availability. So, ScalarDB removes such reliable clock dependencies for better applicability and scalability. This leads ScalarDB to provide a weaker isolation than snapshot isolation, which we call read-committed snapshot isolation, RCSI. So simply removing reliable clock dependency is not great for users. By the way, we've thought about employing a hybrid logical clock, but we decided not to do it. This is because ScalarDB takes client-coordinated approach for managing transactions. So ScalarDB doesn't share information between transaction managers. So employing hybrid logical clock would make ScalarDB introduce an additional database write for each record read to keep track of happened before relation. So we make ScalarDB transactions guarantee strict serializability in different way. So the basic strategy of making transactions strict serializable in ScalarDB is keeping track of anti-dependencies implicitly. Approaches like SSI and SSN take explicit anti-dependency tracking by sharing read sets between transaction managers. But ScalarDB tracks anti-dependencies implicitly by releasing read sets. So specifically, sharing read sets between transaction managers is very difficult in the client-coordinated protocol of ScalarDB. Also, sharing read sets through databases cause too many database reads and writes, which affects the performance badly. So we decided to implicitly track anti-dependencies by reading read sets. This approach is similar to the one employed in recent memory engine like Silo. Our approach is more conservative than SSI and SSN, so it could cause more errors due to false positives, but it requires fewer additional database reads and writes, so it's more efficient. We evaluated ScalarDB with Amazon AWS. We used two workloads, YCSB and TPCC, for this evaluation. We compared ScalarDB with two XA-based products, Atomics and Theta. Let's look at the performance of global transactions. We used YCSB workload F for this evaluation. X-axis is the number of client threads, and the Y-axis the throughput, QTPS. So let's look at the first graph. We use the two MariaDB instances. The blue line is ScalarDB, and the green line is Atomicus, and the orange line is the Theta. As you can see, ScalarDB is a little slower than Atomicus, but we believe it's reasonable performance since ScalarDB achieves database agnostic transactions, unlike XA-based products. By the way, you can also see that the performance of XA-based products are very dependent on how they're implemented. So there are big performance differences between Atomics and Theta. The next one is the case where we use two PostgreSQL instances. Theta couldn't run on PostgreSQL, so there's no range line. So again, the performance of ScalarDB was pretty close to the one of Atomicus, and then ScalarDB was more stable. Also, we used MariaDB and PostgreSQL. Again, the performance of ScalarDB was pretty close to the one of Atomicus. Lastly, we used PostgreSQL and Cassandra. ScalarDB was the only one that can do global transactions spanning those databases. This is the most unique benefit of ScalarDB. Again, it was also pretty stable. Overall, ScalarDB achieved database agnostic global transactions with reasonable performance. We also verified the overhead of strict serializability of ScalarDB. We used TPCC for this evaluation, and we used two databases, MariaDB and PostgreSQL. RCSI is the default isolation level. It's a little weaker than SI, and SS is strict serializability. So as you can see, ScalarDB achieved strict serializability without much overhead. In MariaDB, at most 15% slowdown. In PostgreSQL, at most 11% slowdown. And we also verified the scalability of ScalarDB. We used Cassandra and increased the number of Cassandra nodes to see if the performance of ScalarDB scales as the performance of underlying databases scales. So X-axis is the number of nodes. As can be seen, ScalarDB throughput scaled near linearly as the number of nodes increased. As a summary, ScalarDB is a universal transaction manager for polystores. ScalarDB achieves strong correctness and reasonable performance while providing database agnostic global transactions. I couldn't explain many things about ScalarDB in this presentation, so please read the paper for more details, like performance optimization techniques and critical mechanisms for productization, like mechanisms for taking backups and handling read-only analytical queries and stuff. Thank you very much for listening.